Hi, this is Dr. Scott Friedman in New York, here to discuss this month's focus piece in the Journal of Hepatology, which focuses on a very interesting and emerging field of pharmacogenomics and drug toxicity. Specifically, I wrote the piece commenting on a very interesting article by Clark and others studying the impact of genetics and fatty liver on the organic anion transporter, a protein that is important for the disposition of statins, in particular pravastatin. This group has shown previously that genetics can influence the activity of this transporter and the disposition of pravastatin, and specific variants may be linked to a heightened risk of myopathy and adverse events from this drug. So to model these variants, they used a mouse in which they knocked out the transporter and looked at the disposition of pravastatin, and then combined that with a fatty liver disease model from the MCD diet. Now, everybody knows that the MCD diet is not ideal as a diet for fatty liver disease, but the authors have previously shown that the model recapitulates the human disposition of pravastatin. So in this particular narrow indication, it's a useful model. So when they combined genetic loss of the transporter with a fatty liver disease model, they had a marked increase in pravastatin concentrations. And of course, the implication is that under specific circumstances, genetic variants may converge with fatty liver disease to heighten the risk of drug toxicity to the liver. Now, this is a very important area, and it speaks to the growing field of pharmacogenomics. In other words, how genetics impact on the disposition of drugs and therefore on the potential risk to liver toxicity. This is a huge undertaking, but of course drug-related liver toxicity is one of the most important complications of pharmacokinetics and drug use in the world. And in fact, more drugs are withdrawn from the market after licensing because of drug toxicity to the liver than any other reason. So this is a really important area. Now, what the authors have shown is that genetics plays a role, that it's variable, but if we return to the human condition, we do not know enough about how genetics impact on drug disposition. And therefore, we can't predict with most cases why or how genetics contributes to drug-induced liver toxicity. There are networks around the world that are trying to collect information to help elucidate this problem. In the U.S., it's the Drug-Induced Liver Injury Network, but there are comparable drug toxicity networks in Europe and throughout the world, which together may be able to uncover genetic links to the risk for liver drug toxicity. This is a huge undertaking, but with the advancing ability of big data computing, we're hopeful that there'll be progress in uncovering genetic links and therefore predicting the risk of liver drug toxicity. Now finally, even if we have genetic predictors of toxicity, how are we going to get that information to practicing clinicians? They're not going to be reading very detailed descriptions of drug toxicity and genetic links. And so there are efforts underway to create software that would effectively translate genetic information conferring or describing risk of particular drugs into the patient's electronic medical record. We're just in the early days of such effort, but one can imagine that eventually a patient will go to the doctor will prescribe a specific drug in the EMR, and an alert will sound or an alert will pop up that tells the clinician in this particular patient, because of his or her genetics, the dose needs to be changed or the risk of toxicity may be especially high. So that's where this field of pharmacogenomics is going, both in terms of understanding the risk of genetics, how that risk may be amplified if there's underlying liver disease, in particular fatty liver disease, and ultimately translating complex genetic information into decision-making by clinicians at the point of care. We have a long way to go, but the tools are in place, and this is an extremely important problem that could save thousands of lives if we can avoid drug toxicity to the liver because of genetic variants.